Hello, my name's Tim Sands, and this is my UIUC ECE 470 robotics class extra credit project. I am going to talk about a robot I've been designing. It's been in the making here for a 3D printed farm, 3D printing farm, where what I'm going to do is automate the removal of build plates from printers and hopefully make it so printers can just print infinitely, assuming they have enough material to keep printing with. But we'll get to that. That could be another printer for later. But essentially what I got built so far here is the base plate with the slew bearing. We've got a slew bearing here. I got wire management coming through the base here. There's little ports off to the side. Oh, let me make it easier for you to see that. There's little ports here for the electronics. There's a NEMA 17 stepper motor on this currently. That's going to be a NEMA 23. That's why you see multiple mounting patterns. NEMA 23s are slightly larger, more torqueier. Um, this is a 60 tooth gear here, and its mating gear is right here. This is a split ring planetary gear train. This is one portion of it. I didn't finish printing it here because I was testing to see its fitment. It's actually a perfect fit. Now, what I want to point out to you here is you see how there is even spacing between all the gears here, except for right here, it's closer. That's because there's one less tooth on this than on the orange one. That means this has 59 teeth and this has 60. And what that means is as this is rotating, what's actually happening is this has to rotate 3 times because it's a 3-to-1 planet ratio here. There's 60 teeth here and there's 20 teeth on this tiny blue one in the middle. And what that means is when this rotates 3 times, it offsets this by just a single tooth. And then it rotates 3 times and offsets it by a single tooth. What that gives us is a very torquey, very slow, but very high torque. What I need that for is to be able to pick those build plates from a long distance and then lift up, which means it needs a lot of torque here to overcome all that. Because when you're actually removing build plates from a printer, you do it really close up in person. So moving on to the actual robot here, let's show its zero configuration. That's going to be like this. And what that means, zero configuration, is that the thetas are all zero for anyone that's not in this class and is watching this video. That means the angles are defined to be 0 degrees at this point. So going on to the kinematics here, that would mean theta 1 down here, which rotates about this axis, or straight up and down right here from this view, top view, it would rotate left and right like this. That's that slew bearing that you saw on the base. And then the second theta 2 is it's pivoting about this joint right here, that purple part where this little dot is. And then there's another one up here, theta 2, and there's another one over here, theta 4, and then theta 5 is another knuckle joint that's rotating like this. And then there's theta 6, which is actually um, the clamp. It's going to be measuring how hard or how far it has clamped. You know, what clamping position is that going to be? I guess that's prismatic. I'm not quite sure how I'll model that yet, but we'll get there. Moving on to the forward kinematics here, what we have here is the robot in zero configuration up top. I'm defining 0 to be where this joint 2 position is, and then iterating back 120 millimeters to where the base is. And that's where the S-frame is really located, is on this base over here. And then the third joint here, fourth joint, and fifth, and whatnot. And then where the potential TCP is going to be located, the tool center position, that's its spatial frame for the B frame. And then we have our forward kinematics here, which is a very simple calculation in this situation. And then it's Jacobian down here with this matrix. And then it's a M matrix right here because they happen to be in the same orientation, the S frame and the B frame in this situation. We have our domain of angle range here, and that's just going to be a plus or minus 360 on the base, plus or minus 98 is the maximum that the first actual revolute joint here can produce. I mean, that's also a revolute joint, but I'm considering this to be the first like actual boom that can be moved here. It's considered theta 2. And then we have all the other joints here showing their angles, and that's how I came up with these angle ranges here. Inverse kinematics here is a little more complicated because you actually have infinite solutions when you have this many linkages. It's called redundant solutions at that point or whatnot. I believe it's something along those lines. Don't quote me on it. I'd have to check the textbook again, but the goal for solving that issue is using the Newton-Raphson's method, where I would iterate through after initial guess of where the TCP wants to go and the angles it'll choose to get to that, and it would then iterate through that and converge to a solution of thetas, and then it would use that to create the motion. As far as the coding and the initialization and setup of everything, the way I do it with this robot is I'd have 3 points that are mounted and colored on the bench that's supporting all the printers on the print farm, and then I would home the robot to that position and have a permanent matrix that references that home position to all of the other robots and the rack. So there's going to be predefined location matrix to all those printers and all the racks where all the build plates are located with respect to that home position. And the robot, the way it homes, it's going to also have a camera mounted on the end effector. Let me show that. The end effector here is going to have a camera mounted to it in some way. There's a couple mounts already created for it for bolt holes and whatnot, and electrical contact transfer through a rotary joint here. And what that's going to do is make it possible to visually confirm that I've picked and placed a build plate. And if it failed to place it, I can then use error checking to see, okay, did it actually place it where I wanted it to go? Did it not? And if not, then use Vision System to find out where it went. Like, is it back still at the old printer that I thought I removed it from, or did I drop it? It'll be used for doing that kind of thing. It'll also be used for updating positions of build plates and whatnot. And that about wraps up as far as I've gotten on this robot. Thank you for watching and have a great end of the semester.